Greetings everyone, this is Mr. Mall, and in this video I'm going to show you some simple example problems using a series or a parallel circuit. So I'm going to go ahead and look at example number 8 and 9 from that handout. And so it says three resistors, 4 ohm, a 7 ohm, and a 10 ohm resistor are connected together in parallel, and then we connect these to a 9-volt battery. So I've drawn what this would look like. These are parallel, so I've drawn my little resistors, 4, 7, and 10 ohm, and they're in parallel. So there's going to be three separate branches for current to flow. And so I've drawn my little picture there. You'll notice I also did a little coloring trick. I have another video and talking about the coloring trick, but basically the coloring thing just shows me where the highest voltages are and where the lowest voltages are. So in red I colored where the highest voltage is. I just drew a line and colored until I from the positive end of the battery until I hit a resistor, and there were a couple different resistors. So that high potential, that high energy state exists at all of those locations in my circuit. And then the lowest energy state is at the negative end of the battery. And so I went ahead and connected a blue line until I hit resistors. And you'll see that the entire second half of the circuit is all connected to that lowest energy state. And so we can see that there's only two different voltages in this parallel circuit. So there's one drop, and it's going to be the same for each one of these. You'll notice the color is the same. The color change is the same. So what I want to do is, first off, I need to find the equivalent resistance of the group. Okay, so I look at my equation sheet, and I notice this little guy over here. This little P stands for parallel, and it says the reciprocal of the equivalent resistance of a parallel circuit is equal to the sum of the individual reciprocal of the inverses. So what this is basically saying is that as you add more resistance to your circuit, the overall resistance is going to decrease in this way. So when I rewrite this, so for this circuit, the equivalent resistance is going to be equal to a quarter plus a seventh plus a tenth, and then we're going to get some value here, 0.493, 0.4493. And then once I get this value, in order to get just REQ, we're going to take the reciprocal of this little guy here. And so that's going to give us that the equivalent resistance is equal to 2.03 ohms of resistance. Okay. The next thing we're going to do is it says find the voltage and the current through the 7 ohm resistor. Actually, no, we're still not done yet. It asks us to find the current flowing from the battery. Alright, so I'm halfway there. So the next step I'm going to do is I need to find the I of the battery. Okay, so I'm going to go ahead and do this to the side here because I kind of ran out of room. I of the battery. And so at this point, what I would probably do is I would make, it looks like I'm going to have to solve for some voltage and currents through certain resistors and for the whole battery. So what I'm going to do here is I'm going to make a chart to keep track of everything for this circuit. So this is called a VIR chart, because it has VI and R all involved, VIR. And it also is going to have all the resistors. So we've got resistor 1, resistor 2, resistor 3. And so this is 4 ohms, 7 ohms, and 10 ohms. Alright, so there's my resistances. And then the last column on my VI chart is going to be for the totals. Okay. So what we just did is we calculated the equivalent resistance as being 2.03 ohms. We just calculated that by using that principle relating the resistance as I added resistors in parallel. So I know that. The other thing I can look at is because these are in parallel, and you'll notice the color change is the same, then that means that the voltage drop was the same for all of those. And we saw this in the lab when we had parallel. all those voltage drops were the same. So I'm going to go ahead and throw in my 9 volts as being the potential difference or the voltage across every single one of those resistors. Okay, if you wanted to imagine that this is a slide with, it's a three-way slide. Okay, so you get to the top of the slide and you could go down one of 3 paths in this circuit. And so it's the same way here. The potential energy for each one of those paths is actually going to be the exact same. And so that's our conservation of energy going on there. And then to find the current flowing from the battery, this is this I column, I from the battery, that's going to be equal to the total voltage of the battery divided by its total equivalent resistance. And so the voltage of the battery we said was 9 volts. The equivalent resistance was 2.03 amps, or ohms, excuse me. And so we're going to get that there's 4.4 amps total of current. Okay, so that's where we just did our little, I is equal to delta V over R. There's that little guy there. All right, so we now know the total current the total current flowing through the battery. Okay, 4.4 amps. The next question says, find the voltage and current across just the 7 ohm resistor. Now, remember from the little lab we did, because there's multiple paths, the current through each of these paths is going to be different. It's actually going to be the most current through the path of least resistance in this case. So I'm really going to clue into this little resistor right here, and we're just going to look at that one. So recall a second ago that for the voltage of the entire circuit, because they're all in parallel, the voltage was the same. Okay, so the voltage drop was the same for V1 is equal to V2 is equal to V3 is equal to V the battery. Okay, remember we said that's going to be for parallel circuits. So what we can do then is we can just do the I for the resistor number 7. Okay, so for our little 7 ohm resistor, we're going to look at the voltage for that little 7 ohm resistor and the resistance for that 7 ohm resistor, and I'm just going to plug those values in. 9 volts from our table divided by 7 ohms, and we're going to be looking at 1.3 amperes or amps. And we can solve for just that one circuit element. Now if I go through and do the same exact calculation for the other ones, we're going to see that this is going to be 2.3 and this is going to be 0.9 amps. And what we're going to find out is that when I add up all those currents, because of conservation of charge, the total current through all those junctions is going to be add up to 4.4 amps. Okay. All right, let's look at another example. The next example is dealing with 3 resistors in series. So I drew a little picture here in series. And you'll notice that I did that same little coloring trick, except now there's going to be a lot more voltage drops. It's not going to be the same voltage across the whole thing. Remember when you did that little lab, after one bulb, the next one had less and less voltage to go around. So each one of these resistors is going to cause a drop. And so I signify that with a change in color. And so blue being the lowest after it makes it through all these 3 resistors, and then obviously red being the most. So I look at my equation sheet, and it says find the equivalent resistance of the group. And so I know this is a series circuit, so there's a little RS, and the total equivalent resistance is equal to the sum of the individual resistances. And so we're going to go ahead and add those up. 4 ohms plus 7 ohms plus 10 ohms. So our total is going to be 21 ohms. Feel free to make another VI chart to keep track of everything, because it can be a really helpful way for you to organize a problem as you solve it. And so we're talking about the 4, the 7, and the 10 ohm resistor. And we're looking at the total as being 21 ohms. Okay. All right, so now we know the equivalent resistance. It also asks for the current flowing through the entire battery. And I know that for the entire battery, this is R1, R2, R3, this is our total. We're looking at a 9-volt battery again. Okay. But for a series circuit, remember that the voltage is going to be split between each path. So I'm going to have a voltage drop at each resistor, and in total they're going to have to add up to 9. Okay, so in order to find the I of the battery, it's going to be equal to the total voltage of the battery over the total resistance. So 0.43 amps using Ohm's law is going to go down here. 0.43 amps. And so what I know that's special about a series circuit is just like marbles in a garden hose or traffic in a traffic jam, the rate of flow for an entire series circuit is identical. Okay, it's going to be the same for each. If one marble enters the tube, one comes out. And so I'm going to go ahead and add on here that the current flow for number 7 is equal to 0.43 amps, as long as all the other ones, because I1 is equal to I2 is equal to I3 is equal to I total. This is for a series circuit. So I'm going to go ahead and go through here and put 0.43 amps for everybody. 0.43. Okay, because our current is the exact same. And so now, in order to find just the voltage, well, voltage is just equal to I times R using Ohm's law. Okay, so I'm going to go ahead and solve for my voltage of resistor, the 7 ohm resistor, and that's equal to I times R. So I of the 7 ohm resistor times R of the 7 ohm resistor. And you can call this R1, you can call this, in this case, you can call this little guy R2. It doesn't really matter how you signify what you're calling it. Either way, I'm taking my 0.43 amps, I'm multiplying it by my 7 ohms of resistance. And so my voltage drop for that first little, or for that 7 ohm resistor is going to be 3 volts. 3 volts. Now, all those other resistors have different resistances, so the voltage drops are going to be different. So if I plug in and do the exact same calculation for the other guys using their resistances, I'm going to get 1.72, and I'm going to get 4.3, and what we're going to find out, well, about 1.7, we're going to find out that those are going to all add up to 9 again, proving that the voltage drops as I go around that series circuit are going to all add up to the final voltage, and that's going to show us our conservation of energy as being true. Okay, so this has been some basics, simple circuits, and I hope that this video has been helpful.